Welcome students to the another lecture in LPC 2148. So today we are going to study another serial protocol SPI. SPI is nothing but serial peripheral interface. So today we are going to see another serial protocol for LPC 2148. So let us see what is there inside the SPI. SPI is a general purpose synchronous serial interface. During an SPI transfer, transmit and receive data is simultaneously shifted out and in serially. It means you are having two parallel lines. As in contrast to I2C, in SPI, your data transmission is bidirectional simultaneously. In case of I2C, the same line is used for data in and data out. Only serial data line is available in case of I2C, whereas in case of SPI, two separate lines are available. One for sending the data and one for receiving the data. Okay, so we are having simultaneous data transmit and receive operation available in SPI. So that is the one biggest advantage of SPI. So speed is naturally doubled in as compared to I2C. Then it also requires a serial clock because it is a synchronous communication, synchronous serial communication. So it is requiring a serial clock. Serial clock line synchronizes the shifting and sampling of the information on two serial data lines. So always the data should be sent in synchronization with the clock signal of SPI. Okay. Now, SPI devices communicate using master and slave. So here also you can see that master-slave configuration is available. So one device will act as master and another device will act as a slave. Okay. Due to its lack of, but it is not using the addressing. Means no addressing is available there. So SPI requires more effort and more hardware resources than I2C when more than one slave is involved. So normally you can go for SPI when there are less number of devices present there. Okay. But SPI tends to be simpler and more efficient than I2C in point-to-point applications. Point-to-point means one master, one slave, or one master and more slaves are there. So if you have, that is why it is said that for less number of devices, you should always go for SPI. Okay. For the very same reason, the lack of device addressing means less overhead. So you don't have to every time start the communication with the address of the slave there. Because there is only hardware line is used to connect the slave there. So how it is used, we will see in the next slides. Okay. So how it works? Device communicates using master-slave relationship. Okay, means one device will act as master and another device will act as a slave. When the master generates a clock, when the master generates a clock and selects a slave device, data may be transferred in either or in both directions simultaneously. Means you can have the bidirectional data transfer or you can have unidirectional data transfer in case of SPI. Okay, only thing is it should be synchronized with the clock signal of the SPI module. In fact, as far as SPI is concerned, data are always transferred in both directions. It is up to the master and slave devices to know whether a received byte is meaningful or not. So normally data is transferred in bidirectional mode. Now, what are the features available in case of LPC2148? It is a synchronous serial full duplex communication. It combines SPI master and slave, so you can have both master and slave configuration available. Maximum data bit rate is of 1/8 of the input clock rate and it transfers 8 to 16 bits per transfer. So at a time it can transfer 8 bits or maximum 16 bits it can transfer. Okay. Now, how the connections are done in the SPI serial peripheral interface protocol. So for that, minimum 4 lines are required to connect the two devices. Okay, so actually 4 lines are required. So here the first configuration is shown, single master and single slave. So only one master is available and one slave is available. So it is working with 4 signals. First is serial clock. Okay, so it is given from master to the slave. So always master will give the clock signal to the slave. So it is unidirectional. Next, MOSI. MOSI means master out, slave in. Master out, slave in, from master to the slave. Third signal is, this is the second signal, or this is a data line. Third is again a data line. Okay, what is this? Master input, slave output. The data will transfer from slave to the master. So two data lines are there, MOSI and MISO. MOSI means master out, slave in. MISO means master in, slave out. And the fourth one is SS. SS is slave select line. It is from master to the slave. So these are the 4 lines. So normally I2C is called as two-wire protocol, whereas SPI is called as four-wire protocol. You are using 4 wires to connect the two devices. Okay, so this is the single master and single slave configuration. One slave is connected to the master using the 4 lines SCK, MOSI, MISO and SS. So here the signals are given there. SCK is serial clock signal, MOSI master out, slave in, MISO master in, slave out, and finally SS is slave select. SS is slave select. Okay. Now in the SPI protocol, this is the second type of the configuration, single master and multiple slaves. Okay, so what happens here? Here you can see that for every slave, again I am having 4 wires. Okay, here also I am having 4 wires. Here also I am having 4 wires. Here also I am having the 4 wires. So this is complying the same thing which we have seen in the previous one. Serial clock, master out, slave in, slave out, and slave select is there. But in case of master, as you go on increasing the number of slaves, your slave select signals goes on increasing. Okay, so for every slave, you will require one separate line for slave select. Okay, it means it is decreasing the address sending there. So address sending is not required in SPI, which was present in I2C. I2C मध्ये दोन्हीला when the master is going to give the data or collect the data from the slave, master will always give the address. But in case of SPI, master will not give the address, but it will just activate the signal slave select. It has to make this signal high for slave 1. It has to make this signal high for slave 2. It has to make this signal high for slave 3. So depending upon which signal is high, that corresponding slave will communicate with SPI master. So the number of hardware goes on increasing as the slaves goes on increasing. So if you are having the multiple slaves, your number of address slave select lines will go on increasing. Okay, so this is a single master multiple slaves configuration available in SPI protocol. Then we will see some key points about the SPI protocol. Okay, so the first one is master generates slave select signals. We have seen that this is SS. SS1, SS2, SS3. Number of slave select lines are present. These lines goes on increasing as the number of slaves goes on increasing. Okay, then this consists of old-fashioned bit banging and can be pretty sensitive. You have to time it relative to the other signals and ensure, for example, that you don't toggle a select line in the middle of the frame. So you have to be very careful when you are actually sending the slave select signal. Because if the data is transmitted from the slave, you have to first wait for completion of the data frame. Once the data framing is completed or the frame is received, then only you can go with selecting the other slave. Okay. SPI does not have an acknowledgement. Now, acknowledgement was also present in case of I2C protocol. It will always send one acknowledgement bit there saying that it has received the data correctly. But in case of SPI, it does not have an acknowledgement. So, uh, there is no any confirmation that the data is received properly. You have to just go on sending the data that master or the hmm, either master will send the data or slave will send the data, but in either case the sender will not know that the receiver has received the data. So it is not that much faithful communication we are having. In fact, without a communication protocol, the SPI master has no knowledge of whether a slave even exists. Means the master will just select the slave and it will go on sending the data. So sometimes this may happen that slave is not existing there also. That may happen. SPI also offers no flow control. If you need hardware flow control, you might need to do something outside of SPI. Okay, means how much data you are going to, uh, whether they are having the synchronization with each other or not. To control that, you don't have anything about the SPI. Okay, so these are some drawbacks of SPI. No acknowledgement, no flow control. Now, how the data is transferred using the SPI. Okay, so for that it is using the two things. One is clock polarity and second is clock phase. Now, what is a clock polarity? It decides steady state clock pin when data is not being transferred. Clock polarity. When data is not being transferred, that steady state is given as clock polarity. And clock phase means it selects the clock age that captures data. It selects the clock age that captures the data and allows it to change the state. It selects the clock age that captures the data and allows it to change the state. So remember, you have to always consider the clock polarity CPOL and clock phase CPH. Okay, now how the CPOL and CPHL works, that is given. Okay, clock polarity once again. Steady state, it decides the steady state clock pin when data is not being transferred. Now consider here, this is the steady state. So CPOL is 0 means steady state clock is 0. CPOL 1 means steady state clock is 1. When no data transfer is done, then by default the clock line will be 1. Here the by default the clock line will be 0. So that will depend upon CPOL, clock polarity. Okay, and after that it will toggle high low whenever data transfer takes place. Okay, for example, here the slave select signal is given. When the slave select signal is given, after that the toggling of the clock pin will start. So this, when CPOL clock polarity is 0, it will toggle first from 0 to high, then from high to low, high to low, high to low to high, and so on. And for CPOL is equal to 1, it will start with the first level as high, then from high to low, low to high, again high to low, and like that. Okay, so remember, this is 0 level you are having and this is 1 level you are having. Okay, then we will consider CPHA. Okay, clock phase. Clock phase is equal to 0 here and here clock phase is equal to 1. So what happens when it is 0? When it is 0, you can see that the data is shifted, data is modified exactly at this point. When the clock is 0, it will start. Whereas in this case, where it will start at this level. Okay, means when the transition occurs, after that it will transfer the data. Okay, whereas it will modify the data. Here the data is modified when there is a low level is present there, and here the data is transferred when their clock phase is equal to 0, means when 0 is present there, and here when low level is present there or first level is present there, immediately data must be changed here. Whereas in this case, after the one transition takes place, then the data will be presented here. Okay, data will be modified when CPHA is high. So clock phase high, it selects clock age that captures data and allows it to change the state. Okay, so here when it is 0, the clock age is from 0 to 1. Okay, 0 to 1, if CPOL is equal to 0, at that point, the after that, the data can be modified here. Here, the data is captured. Okay, here you can see that. When you can modify the data, that is decided upon depending upon CPHA is equal to 0 or CPHA is equal to high. Clock phase high and clock polarity. Two things are there: clock polarity and clock phase. Clock polarity will decide what is the steady state of the clock. When you are not transmitting the data, whether the clock will be high or whether the clock will be low, that is decided by SCK signal. Okay, SCPOL signal, and CPHA will decide on which transition the data will be captured. So whether you want to change the data on the rising edge or falling edge, that is decided by CPHA pin. Okay, clock phase pin will decide it. So I hope you have understood the data format. Now we will go to the next thing. Control lines of the SPI. So what are the control lines present in the SPI? One is the chip select or SS. Very specifically, it is SS. The corresponding peripheral device is selected using this pin. Okay, so instead of CS, I will call it as SS. Slave select, you can also say. Okay, instead of chip, you can also call it as slave. So in some cases, you are calling it as chip select. In some cases, you are calling it as slave cases. In our case, we will actually call it as slave select. The corresponding peripheral device is selected. This pin is mostly active low. In unselected state, the SO means MISO. Actually, this is SO. It is referred as SO or MISO also. MISO means master in, slave out. Okay, MISO means master in, slave out signal. So when MISO signal is given, these are high impedance state. Okay, high Z means high impedance state, means neither 0 nor 1. When this is unselected, it is as if disconnected from your master. Master decides which peripheral device it wants to communicate. Okay, the master will decide by you giving the SS signal, slave select 1, slave select 2 or slave select 3. Then the other one is SCL. SCL is not SCK, it is nothing but the clock signal. It is brought to the device whether it is selected or not. The clock serves as synchronization of the data communication. You can see that with respect to SCK, your data bits are given there. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, and this is 8. Okay, like that your data will be transferred. Okay, so with respect to this your bits are transferred. Same thing happens here. With respect to this, your bits are transferred there. So this is nothing but your clock signal is responsible for the synchronization of the data communication. Okay. Then we will see the block diagram of the SPI available in Lpc2148. So what is SPI? Serial Peripheral Interface. What is SPI? Serial Peripheral Interface. So you can see that total 5 blocks are there. The first one is the SPI shift register, which will convert parallel data into the serial one and serial data into parallel one. Then one more block is there, SPI clock generator and detector. Means it will collect the peripheral frequency and from that it will generate the own clock of SPI. You can program it. You can program the clock signal for the SPI using the control register. Then SPI state control register is there where you are giving polarity and phase clock phase signal we are giving. Okay, CPOL and CHA. Then output enable logic. Output enable logic is used for serial clock out enable, uh, master out slave in out signal, master in slave out signal. So for that you are giving these signals there. Okay, and here you are giving the clock signal there. Now what you are having here, this is connected to the different various SPI registers. So registers will control all these things. Here you are giving the different signals which are connected to the peripheral. Master out slave in input signal, master out slave in output signal. Means either it can work as master. When it is in master mode, it will be MOSI in signal is connected. Okay. Or it can also act as slave. When it is acting as a slave, MOSI out signal will be given. Okay. MISO in is again given in the master mode and MISO out is given in the slave mode. So MISO signal will be considered as output for master and slave mode. Okay, so this is the block diagram for the SPI module present in Lpc2148. Now, what are the different registers available in the SPI? Just I am giving you the name of the registers. We are not going in the detail of the registers and programming. This is just for the sake of the understanding of SPI protocol present in Lpc2148. You are not expected to write a program for SPI communication. Okay, so I am just giving you the list of the registers. SPI control register. Okay, S0 SPCR. Okay, it contains a number of programmable bits used to control the function of the SPI block. Next is SPI status register. It contains read-only bits that are used to monitor the status of the SPI interface, including normal functions and exception conditions. The primary purpose of this register is to detect completion of data transfer. This is indicated by the SPI bit, serial peripheral interface flag bit, interrupt flag bit actually. That is, the remaining bits in the register are exception condition indicators. So just to check the condition of the data transfer, you can use the status register. Then the third one is the data register, where you are going to actually put the data byte to be transmitted or the data byte which you want to collect from the SPI module is present in this register. So this is the SPI data register, and the last one is SPI clock counter register. Now what is a clock counter register? It controls the clock rate when the SPI block is in master mode. This needs to be set prior to the transfer taking place when the SPI block is a master. This register has no function when the SPI block is a slave. Okay, now we will see how it works in the master mode. So whenever your LPC2148 IC is used in a master mode, how the master operation works, that is given by these steps. So the first step is set the SPI clock counter register. So it will decide the clock rate. Then set the SPI control register to desired settings. Okay, that is the second. So first one, set the clock rate. Second is give the different settings there, like clock polarity, clock phase, phase signal, whether you want the rising edge controlled clock or falling edge controlled clock, that you can decide there. Okay, then the third one is write the data to transmit it to the SPI data register. So put the data in the data register, that is the third step. This write immediately start the SPI data transfer. It is same as your UART. Whenever you write the data in UART register, it will automatically start transferring the data. Similarly, whenever you put the data in the SPI data register, the transmission of the data will start. Okay, then the fourth step is wait for SPIF bit. What is SPIF? It's the interrupt flag bit. This is set when the data transfer is completed. Okay, so how it is set? SPI, wait for the SPI bit in the SPI status register to be set to 1. The SPI bit will be set after the last cycle of the SPI data transfer is completed. So whenever the last cycle of the data transfer of the SPI is completed, SPIF bit will be set to 1. Okay, so whenever it is 1, then what you have to do? Read the SPI status register. Read the received data from the SPI data register. Of course, this is in case when master wants to read the data from the slave. Okay, and the last one is go to step 3 if you are having more data to be transmitted or to be received. So you have to first set the clock rate, then give the settings, then write the data and wait for the data transmission. It is similar to your UART working. In case of UART also you are doing the same thing, but the only difference here is it will also initiate the clock signal to be communicated with the slave. So this is about the master operation of SPI protocol or SPI module present in LPC2148. Okay. Then we will go for the slave operation. Now slave operation is bit easy than as compared to the master operation, because in master operation master has to initiate the thing. In slave operation, what it has to do? It has to do first it will set the SPI control register to the desired settings. So it's the first step. Then write the data to be transmitted to the SPI data register. So it will write the data to the SPI data register. Okay. If it want to send the data. Note that this can only be done when a slave SPI transfer is not in progress. So before transfer, if the transfer is not completed, you cannot write the data in SPI register. So for subsequent data sending, you have to take care of this thing. Then wait for the SPI bit in the SPI status register. So naturally we are talking about the transmission of the data in slave mode. Okay, wait for the SPI bit. This is the third step. Wait for the SPI bit in the SPI status register to be set to 1. The SPI bit will be set after the last sampling clock age of the SPI data transfer. Then the fourth one is read the SPI status register, read the received data from the SPI data register and go to step 2 if more data is required to transmit. So here there is no need of setting the clock rate. You will set the clock rate in the master mode only. Rest other things are almost same in case of master as well as slave. Only thing is you have to decide whether you are going to transmit the data or you are going to receive the data. So I hope you have understood how the SPI works. So basically, this is a four-wire protocol. It is not having the overhead of acknowledgement bit, neither of the address bit, but it is increasing the hardware. So it is recommended that you use the SPI protocol when you are having the less number of devices to be connected to the controller. Okay, so this is a four-wire protocol, and it works again. It works in this master and slave mode. One master is present there, one slave, more than one slaves are present there. For every slave, you are having one slave select signal present. Okay, so this is all about the SPI protocol, and we will stop here. Thank you, students.